Hello students, welcome to the digital classes. In the earlier classes, we have discussed electricity and we have discussed Ohm's law. Also, we have discussed heating effects of current. In this class, we will discuss electromagnetism. It was thought that electricity and magnetism are completely different concepts until Ørsted's experiment. Hans Christian Ørsted has discovered the magnetic effect of electric current. Ørsted's experiment paved way to the branch of physics that relates electricity and magnetism. This is electromagnetism. Ørsted's experiment led to several other important discoveries and inventions such as electromagnetic induction, dynamo, etc. Before we look into Ørsted's experiment, let us have a look at few things like magnetic compass, bar magnet. This is a magnetic compass. This is a magnetic needle, it is a magnet. It is pivoted at the center and it is free to rotate in this plane. This one will always point north south. In other words, we can say this will be aligned itself in the direction of any magnetic field. This magnet will get deflected by another magnet, or it will also get deflected by another magnetic substance. It will get deflected by another magnetic substance. So, magnet is getting attracted to a magnetic substance, or it is getting attracted to another magnet. So, this is a bar magnet, and the white dot here, the white dot in the bar magnet shows the north pole and the other pole will be south. So, the compass will get deflected by a magnet. Let us see what is a magnetic compass. Magnetic compass is a device that shows north-south direction. A thin magnetic needle is pivoted at its center and it is free to rotate. Here is a magnetic compass. We have magnetic compasses in mobile phones too. It always points towards magnetic north pole, which is little away from geographic north, that is the direction of Earth's magnetic field. We can also make a magnetic compass by using a bar magnet. It gets deflected by another magnet or another magnetic material. Let us see various magnetic substances. Magnetic substances are those that are strongly attracted by magnets. We can classify substances into three categories: those which are strongly attracted by magnets, which are weakly attracted by magnets, and weakly repelled by magnets. Those which are strongly attracted by magnets are ferromagnetic materials, which are weakly attracted by magnets are called paramagnetic materials, and those which are weakly repelled are diamagnetic materials. We will discuss those substances which can be made into magnets, that are ferromagnetic materials. Here are some safety pins. If we take a pin and try to touch another, they will not attract, because though they are magnetic substances, they are not magnets. If we take a magnet and touch a pin, it gets attracted to it. Also, now the pin acts as a magnet and it tries to attract other pins. Here we can see the pin which is in contact with the magnet acts as a magnet. It will repel another like pole, it will attract another unlike pole. We can see that the pin is repelling magnetic pole. These can be made into permanent magnets. Only ferromagnetic materials can be converted into permanent magnets. We see various permanent magnets in different shapes and sizes. The one which we use in labs are bar magnets. We also use circular magnets in speakers. We use horseshoe magnets, etc. This is a bar magnet. Now let us see magnetic field around a bar magnet. Now place the magnetic compass near the north pole of the bar magnet. We can see that south pole will be directed towards north pole of the bar magnet and the north pole of the magnetic compass is pointed away from the north pole of the bar magnet. Now mark the position of the north pole of the magnetic compass. Now remove the compass and place in such a way that the south pole of the magnetic compass is at this marked point. Now mark the position of the north pole of the magnetic compass on the paper. Now remove the compass and place in such a way that the south pole of the magnetic compass is at this previous point. Repeat the process till we reach the south pole of the bar magnet. Similarly, draw more lines of magnetic field around the bar magnet. So the magnetic field lines around the bar magnet appear to be like this. The magnetic field around a bar magnet is as shown in the figure. The magnetic lines of force will come out of north pole and enter the south pole outside the bar magnet, whereas the magnetic lines will be from south pole towards north pole inside the bar magnet. Now let us see the activity to observe the magnetic field around a bar magnet by using iron filings. We need to take a sheet of paper and sprinkle iron filings on the paper. Now place a bar magnet and then slowly tap the paper. We see the iron filings will get arranged in the form of the magnetic field lines around the bar magnet. We can also draw the magnetic lines of force around the bar magnet by using a compass. So we need to take a paper and a magnetic compass and a bar magnet, and then we can draw the magnetic lines of force as follows. We need to remember that the magnetic lines of force are closed loops. A point to be noted that the magnetic field lines are closed loops. Magnetic field lines always form closed loops. This is because north pole and south poles occur in pairs. We never find an isolated pole, that is, we cannot find a north pole separately or a south pole separately. The direction of magnetic field lines outside the bar magnet are from north pole to south pole, whereas inside the bar magnet the magnetic field lines will be from south pole to north pole. Now always we need to understand that magnetic field lines are directed towards south pole. Now we have to mention the direction of any magnetic field line. What about the direction which is perpendicular to the plane? For example, on this plane, if the magnetic field line is coming out or going in, how do we represent it? How to represent direction into the paper or out of the paper? To represent direction out of the paper, we use a dot, and to represent the direction into the paper, we use an arrow. So any direction which is coming out of the paper must be represented by dot, and the direction into the paper by a cross. Children, if you feel that it is difficult to remember whether a cross represents into the paper or out of the paper, I will give you a tip. Imagine you have an arrow which is coming towards you will be pointed. So any direction which is coming towards you will be dot, and if arrow is going away from you, you will see from behind, that is a cross. So a direction coming towards you will be a dot, a direction which is going away from you will be a cross. Children, now let us see Oersted's experiment. This is the setup for Oersted's experiment. Oersted has arranged a wire with a battery and then a magnetic compass close to it. Here the magnetic compass always points towards geographic north. When current is flowing in the wire, Oersted observed that the magnetic compass got deflected and the direction of the magnetic compass has changed. So as long as there is no current, the magnetic compass was pointing towards north. When there was current, the magnetic compass direction was changed. So in this activity, you can observe that when current flows in the wire, the direction of the compass is changing. The compass needle is getting deflected when there is current. So, Oersted has observed that a current carrying conductor is producing magnetic field, and it is because of this magnetic field the direction of magnetic compass is getting changed. So, a current carrying wire has a magnetic field around it. So, this is the conclusion from Oersted's experiment. A magnetic field around a current carrying wire. Children, if a wire is producing magnetic field around it, then we can imagine the shape of the magnetic field lines. This should be circular because of symmetry. If current is flowing in a wire, then the magnetic field line around it must be circular. But what about the direction? The direction of the magnetic field line around a current carrying wire will be known by right hand thumb rule. So, imagine a wire in which the current is flowing, and if we hold the wire by using right hand such that the thumb points the direction of the current, then the curled fingers will show the direction of the magnetic field around the wire. So, the magnetic field line which is produced due to current will be in the form of a circle, and the direction is given by the right hand thumb rule. Right hand thumb rule. If current carrying conductor is held by right hand such that the thumb points the direction of electric current, the curled fingers point the direction of magnetic field around the wire. What is the shape of magnetic field lines around a current carrying wire? Due to symmetry, they must be circular. Children, let us do a virtual activity. So, imagine a wire is set up as follows. A wire is set up through the table and it is connected to a battery, and in the table we can see that the direction of magnetic field lines will be perpendicular to the wire and it will be circular in shape. Children, if the current is coming out of the paper, then the direction of the magnetic field there will be given by right hand thumb rule. So, current is coming out of the paper, we can see the direction of magnetic field lines will be anti-clockwise, whereas if the current is going into the paper represented by a cross, then the magnetic field lines will be clockwise. So, if current is going out of the paper, then the magnetic field lines will be anti-clockwise, and if current is going into the paper, then the magnetic field lines will be clockwise. Now, children, let us see the magnetic field produced by a coil. That is, instead of a straight wire, we bend it. If the wire goes into a form of a circle, then the magnetic field produced inside it will be given as follows. What is the shape of the magnetic field lines around the circular coil? So, imagine a circular coil which is set up this way, and let us say a current is supplied into the coil as follows. Then around the wire at each and every point there will be a magnetic field which will be set up, and exactly in the center the magnetic field will be perpendicular to the plane and it will be along the axis this way. So, the magnetic field will be perpendicular to the plane and it will be along the axis. Children, now if the same coil is made into a solenoid, that is in the form of a helical shape, then what will be the magnetic field? The coil is made into a solenoid, then at each and every point, each and every coil, the magnetic field will be perpendicular and it will be through the solenoid. So, the magnetic field will continue and it will be parallel inside the solenoid. If we observe, the magnetic field inside the solenoid will be parallel and it will be strong, and outside the solenoid the magnetic field will be similar to a bar magnet. So, the magnetic field produced by a solenoid and the magnetic field produced by a bar magnet are similar. Children, now let us revise. The magnetic field around a bar magnet will be from north pole towards south pole, and the magnetic field inside the bar magnet will be from south pole to north pole. The Oersted experiment. From the Oersted experiment, it is found that the current carrying wire produces magnetic field, and this magnetic field will deflect the compass. So, whenever current flows in the wire, magnetic field will be produced. A current carrying wire has a magnetic field around it. The magnetic field around a current carrying wire is given by right hand thumb rule. If current carrying conductor is held by right hand such that the thumb points the direction of electric current, the curled fingers point the direction of magnetic field around the wire. The shape of the magnetic field lines around a wire which is going out of the page, the magnetic field will be anticlockwise, and the magnetic field around a wire through which the current is going into the page, the magnetic field will be clockwise. The magnetic field around a circular coil will be perpendicular to the page and it will be along the axis. If a magnetic field is considered in a solenoid, the magnetic field will be parallel inside the solenoid, as well as it will be similar to the magnetic field produced by a bar magnet. The magnetic field around a solenoid will be like this, which will be similar to magnetic field produced by a bar magnet. Children, in the next class, we will discuss electric motor and electric generator. We will see how a motor runs when we supply electric current. Also, we will discuss how electricity is generated from a generator. Electricity and magnetism are interlinked. From electricity we can get magnetism, from electricity we can get magnetic field, and from magnetic field we can get electricity. So, all these interesting topics will be discussed in the next class. Until then, thank you.
వేసవిలో మనం సాధారణంగా చూసే సమస్య వడదెబ్బ.